Hello everyone, and welcome back to another GIS lecture video. And in the last video, we left off with the cliffhanger of how do we interpret this value for dealing with nearest neighbor distance. And so in this video, I want to wrap up this discussion of interpretation by finishing the subtraction, which we actually didn't do at the end of the last video, and talk about statistical significance. Okay? So first of all, let's just quickly do this subtraction, which we didn't do. We talked about how to interpret the difference, but we never actually calculated it. So if we take our average observed distance, which is 4.40, and we subtract off this average expected distance, which is 3.87, we get a distance value of 0.53. Okay? So this is the number that we would then plug into this sort of interpretation grid here. So we say it's positive, there's a positive difference, and so this might indicate dispersion, right? But you might be looking at this and saying, well, okay, it's positive, but its absolute value, it's not very large, right? It's less than 1. And so you might be asking yourself, okay, well, how do we know if this is even important, right? This is pretty close to 0. How do we know that this isn't just a small deviation, an insignificant, if you will, deviation from random? Well, to do that, we have to do the statistical hypothesis test, right? We have to calculate the test statistic. And in this case, what we're going to do is we're going to calculate what's called a Z-score. Right? And so for those of you who are familiar with the concept of a Z-score, what you do to calculate a Z-score is you take the number minus the mean divided by the standard deviation, right? This is the traditional Z-score. The way that we're going to calculate Z-score is going to be much the same, and so that it can in fact actually be interpreted the same. And the way that we're going to calculate Z-score here is we're going to use our DO, right? This is going to be our X in this particular example. Our X bar here, we're going to use our observed. Well, what are we going to use for standard deviation? Well, for standard deviation, we're going to use something called standard error, right, which we'll abbreviate as SE. Right, so we've already seen this part. This part is the same thing that we just did in terms of subtracting. But this standard error, this piece is new. Right, this standard error piece is new. So let's go ahead and label this. This SE, this is going to be our standard error. So standard error is actually a pretty easy thing to calculate. The equation for standard error is simply just a constant, again, because you see a lot of constants come up in equations like this. 0.2, 0.2, 6, 1, 3, 6. Again, this is just a constant divided by the square root of n squared over a. Right, we've already seen all of these pieces before, right? We have a constant. We have the area of the study area, and then we have the number of points. Right. So all we have to do to figure out the standard error is just plug everything we already have into this equation. So for our specific example, right, our standard error for our specific example is going to be that 0.26136 over the square root. The number of points we have is 15 squared, and our area we already calculated to be 900. So hopefully none of these numbers are new to you. You can kind of see the area came from the area of the study area, and the 15 points we already calculated. So if you do the sort of arithmetic here, you get a value of 0.5272. Right, so this is our standard error. So then we would go ahead and we would plug that back into this equation, right? So this standard error here is going to go back into there. So we already have our D observed minus our D expected. So we would just take 0.53 divided by 0.52272. And if we do the math on that, we get a value of 1.014. Right? So our z-score for this particular example is 1.014. Okay, so we have a z-score. Now what? Well, z-scores are actually a very powerful statistical distribution. All right, and so what we can do here, I'm going to give us a little bit more room. I'm going to draw, to the best of my ability, a normal distribution, right? So a z distribution, right? It follows a normal distribution. But what makes the z distribution useful is that its mean is 0. And we know from experience with normal distributions, right, that we can go some standard deviations away from the mean to get a confidence, right? The more standard deviations we are out, the more confident we can be that that value is going to be within that range, right? And so if our z-score is beyond a certain distance, then we can be confident, right, based on the idea of this normal distribution, that the value that we got is statistically extreme enough to be considered significant. Right? And so typically what you want to do is you want to look for a z-score lower than negative 1.96 or higher than 1.96, right? If you're lower than negative 1.96 or higher than positive 1.96 when you convert to z-score, that means that the value that you've calculated is more than likely not part of this distribution, meaning it is statistically significantly different from what you would expect from this distribution, okay? So to sort of wrap this up, what you're going to do is you're just going to compare your z-score to the threshold value or values, I should say, negative 1.96 and positive 1.96. Right? And these two values, these are 95% confidence. Right? There's a table of z values that you could use if you wanted a different confidence level, but at the 95% confidence level, which is what most applications call for, these are the two threshold values. You either want to be lower than this or you want to be higher than this, right? So if you are lower than this, then you're statistically clustered. If you're higher than this, then you're significantly dispersed. And if you're in between, then you're not statistically, your pattern is not significant. So, all right, let's go ahead and repeat that, right? If less than negative 1.96, you are statistically significant. You're significantly clustered. Right, again, your z-score is less than the threshold for what would be considered significant. right? If your z-score is more than 1.96, right, then you are significantly dispersed. If between, right, negative 1.96 and 1.96, not significant. Okay, right. Hopefully that makes sense. This idea that we can use this equation here. I'm going to slide back over. Right, that we can use this equation here to convert from our difference to a z-score. And that we can use the concept of z-score and the concept of the z-distribution to determine critical thresholds beyond which our result is significant. At the 95% confidence interval, we choose a negative 1.96 and a positive 1.96, and then we just simply compare them to test for significance. So to wrap this video up, let's go ahead and compare our results to these thresholds. So just to recap, the result that we calculated is right here, 1.014. Well, it is less than 1.96, but it is more than negative 1.96. In fact, it's greater than 0. Right? So what we would conclude from all of this work here is that we do not have a significant pattern. Right? We do not have a significant pattern. Okay. Hopefully this all made sense. And as always, if you have any questions, please reach out. Thank you.